And let's see here. I want that and that. Okay. Yes. All right. One of the common problems that have been missed is number 4. And this is something I usually go over in class all the time too. Kids don't necessarily make the connection with the coefficients and the rates. So it says here, for the following reaction, the average reaction rate of A is 0.50 molar per second. What would be the average reaction rate for each of the following? So for this one, you are going to use the coefficients. You're just going to take whatever that coefficient is and multiply it by the rate of A. So for B, you had a coefficient of 2. So it'd be 2 times 0.50, which ends up being 1.0 molar per second. For C, you had a coefficient of 3. So it'd be 3 times 0.50 molar, which comes out to be 1.5 molar per second. And for D, you had a coefficient of 2. So it's going to be 2 times 0.50 molar, which comes out to be 1.0 molar per second. I don't know why that looks like an L, but it does. It's just like writing on a smart board. There we go. So that's what I meant by looking at the coefficients for figuring out the average reaction rate. Let's see here. I think students seem to be doing pretty well with those concepts there. Reaction mechanisms. For the most part, kids are doing pretty well with like interpreting the graph. One of the main ideas though I keep seeing is for like letter C, why is this a rate determining step? So kind of starting in the beginning, how many steps would be in the reaction mechanism for this reaction? Well, you have 3 peaks. So you're going to have 3 steps. The rate determining step is the last step here. Now we can't tell that that's the slowest step by looking at the graph, but that's what most kids are telling me, like for the answer for letter C. Why is this a rate determining step? Because it's the slowest step. Well, we know it's the slowest step because it has the highest peak or the highest activation energy. The higher that activation energy is, the greater the wall to overcome for the reaction to occur. So it's just like if you were running a race. If you had to climb over a really tall wall, the tallest wall is going to be the one that's going to slow you down the most. So that's what I was looking for in question C there. How many activated complexes are shown? Well, you have 3 peaks. Each peak represents an activated complex, so you have 3 of them. And then this reaction here is exothermic. When the energy of your products down here is lower than the energy of your reactants to the left, then you have an exothermic reaction. For 15, I had a lot of people not do the overall reaction. I don't think they noticed that problem there. But it's really important you know how to figure out the overall reaction because you're going to have 2 questions like that on your test tomorrow. To figure out your overall reaction, the first thing you want to do is cancel out substances you see on both sides of the reaction. For example, D2 is a reactant in one step and a product in another step. 2AD is a product in one step and reactants in other steps. BD is a product in one step and a reactant in another. And CD is a product in one step and a reactant in the other. So what we are left with here is A2 plus 2BC, forgot the 2 there, turning into 2AC and B2. So that would be our overall reaction there. Rate determining step is our slow step, so that's going to be step 3. Now, the catalyst is a substance that starts as a reactant and ends as a product. The substance here that starts as a reactant and ends as a product is D2. D2. So that would be D2. Sorry, I'm just trying to get a different color here. I don't even know if it took it for me. For intermediates now, they start as a product and end as a reactant. So AD does this, BD does this, and CD does that. So AD, BD, and CD all start as products and end as reactants. So those would be our intermediates. Now, normally for question D, I have you guys draw a energy diagram for me, but because of our limitations with paper and all that kinds of stuff, I just had you describe it. So it says, how many peaks would this graph have? Well, you had 4 steps, so it would have 4 peaks. And our tallest peak is going to be our rate determining step, which is step 3, because that was our slow step. That would have the highest activation energy there. All right, 16 is a very common question. It was a common question on our homework as well, something like this one. So the rate law for a reaction between reactant A and B is second order overall. If reactant A does not affect the reaction, what is the rate law for this reaction? Well, if A does not affect the reaction, that means A is 0 order. And if it's 0 order, we do not include 0 order in our rate law expressions. So don't write that as part of your rate law expressions. So it's going to be rate equals K times the concentration of B. If it's second order overall and A is 0 order, then that means B has to be the second order. Overall orders are the sum of your orders. So 0 plus 2 would be 2 there. So that's where that second order overall is coming from. For 17, this is another one I saw a lot of mistakes on. A lot of people got A and B correct, but the specific rate constant calculation, a lot of people got that one wrong. So I'm just going to walk through this one real quick here. A very common mistake I see is that students are not making sure the other substance is constant when they are calculating order. So what I mean by that is like, all right, the first one I'm looking at NO. Now, if I'm going to look at NO's data, I have to make sure that hydrogen is constant during that time. So the rate is changing only because I'm changing NO, or nitrogen monoxide there. So in trials 1 and 2, hydrogen is constant. So that's where I would go and compare the data there. So it's going to be 8.0 times 10 negative third divided by 4.0 times 10 to the negative third. We always want to take the bigger number divided by the smaller number. So we're not working with fractions or decimals. That makes our lives easier. That's going to be to some x power. And that's going to equal the rate from trial 1, or trial 2 rather, 4.8 times 10 negative 5 divided by 1.2 times 10 to the negative 5. So 8 divided by 4 is 2 to some x power, and 4.8 divided by 1.2 comes out to be 4. So x here is 2, and that's to the power of 2 squared is equal to 4. A lot of kids are interpreting it as 2 times x equals 4. It's not. It's to that power. Now, in looking at hydrogen, we can only look at hydrogen when nitrogen monoxide is constant. Nitrogen monoxide is constant for trials 1 and 3 there. So then we're going to look at trials 1 and 3 for hydrogen's data. So we're going to take bigger number, trial 3, 4.0 times 10 to the negative 3, divided by trial 1, which is 2.0 times 10 to the negative 3. And that is some x power. And that's going to be equal to 2.4 times 10 to the negative 5th divided by 1.2 times 10 to the negative 5th. So we get 2 to the x power equals 2. Therefore, x is equal to 1 here. So it is first order with respect to hydrogen. When you write your rate law, don't forget to write rate equals K. I have some people forgetting to write rate equals K. It's going to be nitrogen monoxide to the second order times hydrogen to the first order there. Now, to calculate the specific rate constant, that means I'm finding K here. I got to get K alone. To get K alone, I have to divide by NO2 and H2. So I'm just going to erase this so I can kind of make it easier to, I don't have much space here. All right. So then K is going to be the rate divided by NO to the second power times H2 to the first power. So then K is going to be, and we're going to use the data from trial 1, 1.2 times 10 to the negative fifth molar per second divided by nitrogen monoxide. There's 4.0 times 10 to the negative third molar, and that value is squared. And hydrogen is 2.0 times 10 to the negative third molar there. All right. That number came out to be 375. A lot of you wrote 375, but with sig figs, that should be 380 there. And then as far as the unit there goes, you have molarity per second divided by molarity squared times molarity, which is molarity cubed. So we want to clean that up and multiply by the reciprocal. So that would be 1 over m cubed. And when we do that, that m cancels, and that's going to become a 2. So our final unit there would be 1 over s times m squared. Or you could write it 1 over m squared times s. Either way you write it is fine. So that would be our final answer there for K. The overall rate order for the reaction, you add up our exponents. So we're going to add up 2 plus 1, which is 3. So it is third order overall there. Sorry for the small space. I should have made this space much bigger here. People are really struggling with 18, and I think it's because I have so many trials there, and they're not looking to make sure the other substance is constant. So if I'm looking at A, I have to make sure that D is constant during that time. D is constant for trials 1 and 3. So for A, I'm going to compare trials 1 and 3. I'm going to take the bigger trial, 0.50, divided by the smaller trial, trial 1 there, which is 0.10, to some x power. The rate for trial 3 was 1.0 times 10 to the negative second. And the rate for trial 1 is 4.0 times 10 to the negative fourth. That comes out to be 5 to the x power equals 25. A lot of people are telling me x equals 5. That would be true if it was 5 times x, but it's 5 to the x power. So x here is really 2 because 5 squared is 25. What is the order of the reaction with respect to D? So now to look at D, I have to make sure that A is constant. A is constant for trials 3 and 4. So I'm going to look at D's data for trials 3 and 4. So again, bigger number divided by smaller number, 0.50 divided by 0.10 to some x power. And that is going to equal 1.0 times 10 to the negative second divided by 1.0 times 10 to the negative second. Therefore, the rate does not change there. When the rate does not change, you have a zero order reaction. 5 to the 0 power is equal to 1. When you have a zero order, you do not include that in your rate law expression. So this is just going to be A to the second power then. And don't forget, rate equals K. A lot of people are not typing that. They're just writing the A to the second power there. So rate equals K times A to the second power. To calculate the specific rate constant, I have to get K by itself. To get K by itself, I'm going to divide by A to the second power. So then we have rate divided by A to the second power. My rate for the first experiment was 4.0 times 10 to the negative fourth molar per second. Oops, I forgot my squared there. And my concentration of A was 0.10 molar, and that value is squared. K for this one came out to be 0.040, and you have a molarity per second divided by molarity squared there. So it's the same as multiplying by the reciprocal. So molarity per second times 1 over m squared. The m here cancels and becomes a 1, and that squared then cancels. So the unit you have left over is 1 over m times s, or 1 over s times m. And this would be a second order reaction overall. 2 plus 0 equals 2. So that's why it's second order overall. Let's see here. Go back to the meeting. And I'm going to stop presenting. All right. How are we doing? Any questions on what we just looked at there?